All right, so we're in section 4.3, and what we're doing here is we're looking at what the derivative of a function, the first and second derivative of a function, can tell us about the shape of the graph of that function. And we're going to start with a theorem that we've kind of been using already, which is basically if you have a function where its derivative is positive at a point or positive on an interval, then we know that the function is increasing on that interval. And on the flip side of that, if the derivative is negative at a point or negative on an entire interval, then the function is decreasing. We've used this fact numerous times, but we've never actually proven it. We've just used kind of an intuitive argument using the slopes of those tangent lines. Because again, if a function has a positive derivative at some value x, that means that the slope of the tangent line there is positive, which is going uphill from left to right. That implies that it's increasing. Okay, but proof in mathematics requires more than that kind of an argument. So the reason this is appearing here is because the actual proof of this argument relies on the mean value theorem, which we just covered in 4.2. So let's take a look at that. Once again, we're going to call this the increasing and decreasing test. If f prime of x is positive, greater than 0, on some interval, then f is increasing on that interval. If it's negative, f prime of x is negative on an interval, then f is decreasing on that interval. So the proof of it looks like this. Let's suppose that we have this interval that we're referring to in either a or b here. And let's pick any two numbers in that interval, x1 and x2, such that x1 is less than x2. This implies that these are different values. Okay? Now, by definition, and this goes back to section 1.1, which we didn't cover in this class, but this is covered in pre-calculus, and it's not hard to see where this definition comes from. But by definition, an increasing function, or a function that's increasing on an interval, is defined such that for any two numbers in that interval, where let's say x1 is less than x2, f of x1 is greater than or less than f of x2. So in other words, taking f of both sides of this keeps this inequality the same. That's how we define an increasing function. And if you want to, I guess I can kind of create a little illustration as to why this is the case. So for example, here's x1 and here's x2, right? If we want our function f to be increasing from here to here, and let's say f of x1 is right there, we need to be going up in some way from this point to the next point. So for example, this is increasing right here. But notice, because we're moving up from this point to that point, f of x2 would have to be greater than f of x1. So that's kind of where this definition is coming from. Okay, so we want to show this because we want to show that under the assumption that f prime of x is positive on this interval, we want to show that f is an increasing function. So we need to establish this inequality somehow. Okay, so we're going to take f prime of x is greater than 0 as a given because we're assuming that the derivative is positive on this interval. And we know that f is differentiable on this closed interval because we're assuming that f prime of x is greater than 0 on that interval in the first place. That would imply that f prime of x exists, which means that f is differentiable. So that's implicit in that assumption there. By the mean value theorem, then, we would also have continuity on this interval because differentiability implies continuity. That allows us to use the MVT. According to the mean value theorem, there's going to be some number c in this interval between x1 and x2, such that f of x2 minus f of x1 is equal to f prime of c times x2 minus x1. Now, on the right-hand side of this, we have assumed that f prime of x is positive on this entire interval. Okay, so that means that c, which is found in this interval, when we plug it into f prime, should produce a positive number. So this guy right here is positive. On top of that, x2 minus x1 would also be positive because we assumed that x2 is greater than x1. So that has to produce a positive number. That means the right-hand side of this is a positive times a positive, which would be positive. So we could write f of x2 minus f of x1 is greater than 0. That's to say that it's positive. Or equivalently, if I add this term over and then switch the sides that the inequality is appearing on, f of x1 is less than f of x2. That's proving what we set out to prove. So therefore, f is increasing on that interval. B, which is where we want to prove that if f prime of x is negative on an interval, then f is decreasing on that interval, would follow a very similar proof with some inequalities flipped different ways. So we're not going to go through a proof of that. Okay, so now that we've established that as a theorem, this fact that we've kind of been using already, let's do an example with it. I'd like to find the intervals on which this function, y equals x cubed minus 6x squared minus 135x, is increasing and where it is decreasing. I don't know how I did this, but I forgot to type this part when I printed these notes, so that's why it's handwritten in there. According to this increasing and decreasing test, the way that we can determine where this is increasing and where this is decreasing is by looking at where its derivative is positive and negative. So I need to start by finding the derivative. Okay, y prime is equal to, this is a very straightforward one, 3x squared minus 12x minus 135. Okay? And then what I'm going to do is, before I start looking for positive and negative, I'm just going to start by setting it equal to 0. Okay? So this is equal to 0. And if I were to divide both sides of this by 3, because that's the greatest common factor in that polynomial, I would get x squared minus 4x minus 45 equals 0. And that factors down to x plus 5 times x minus 9 equals 0, which implies that x is equal to negative 5 or 9. Now, this is only where the derivative equals 0, which means at all other real numbers, it's either greater than 0 or less than 0, positive or negative. And so what I do with an inequality like this is I take a number line like that, and I find these two values on that number line, negative 5 and 9. And now what I'm going to do is I'm going to pick test points in each of these 3 subintervals that I've just created in the number line, plug them into my derivative to determine whether we're getting positive or negative numbers. That determines what's happening on the entire interval. So for example, right here, if I take negative 5, I'd like to pick a number that's smaller than negative 5. Let's just say negative 10. That would be in this interval. And I'm thinking of that as a test point. I need to plug negative 10 into this derivative and see whether I get a positive or negative result. Now, rather than plug it into this version, it's going to be easier for me to plug it into this one right here. Now, this is not exactly equal to this because we divided by 3, so let me do this instead. I'll keep the 3 there because it's not going to change any results. But now this expression is exactly equal to this one. So if I'm plugging negative 10 into this polynomial, I'm going to get the exact same thing as if I plugged it in right here. But if I do it here, it's a little bit easier to do mentally. And the reason for that is because I can just think about whether each factor in this product is positive or negative. So 3 is a positive number. It's not going to change no matter what x is. If I put a negative 10 in for x here, negative 10 plus 5 is negative 5. It doesn't really matter that it's negative 5. All that matters is that it's negative. So negative 10 here makes a negative factor. Plugging a negative 10 in here, negative 10 minus a positive number would have to be negative, so I have a negative here. Positive times negative is positive. So what that means is that f prime of x is positive on this entire interval. If it's positive for one test point in that interval, then it's positive everywhere throughout that interval. What about here? I need a test point, a number between negative 5 and 9 to plug in. Let's use 0. If I plug 0 in, I'm going to get 3 times 5 times negative 9. That's a positive times a positive times a negative, which is negative.